I'm Swarupa Zail, course instructor for fluid mechanics. In this presentation, we will learn about analysis of fluid motion. Under that, we will learn continuity equation. A fluid motion is analyzed by the application of fundamental equations, and those equations are: first one is continuity equation, second is energy equation, and last one is momentum equation. And all these three equations are based on three fundamental laws, which are law of conservation of mass flow, second is law of conservation of energy, and third one is law of conservation of momentum. So continuity equation is based on law of conservation of mass flow, energy equation is based on law of conservation of energy, and momentum equation is based on law of conservation of momentum. Now we will find out what is the law of conservation of matter. It states that matter can be neither created nor be destroyed, but it can be changed from one form to another form of matter, and this can be done by chemical process. But in fluid mechanics, we do not consider any chemical activity, so this law reduces to principle of conservation of mass, which is applied to fixed volumes called as control volume. So here in this figure, we can see a control surface which is shown by dashed line, within which we can see the control volume. So there is a flow of liquid into this control volume, which is referred to as inflow, and outflow is the fluid leaving the control volume. For a closed system, mass of the system remain constant during a process. But for control volume, mass can cross the boundaries. So we must keep the track of the amount of mass entering and leaving the control volume. The conservation of mass principle for a control volume CV can be expressed as total mass entering the control volume minus total mass leaving the control volume will be equal to net change in mass within the control volume. So here in this control volume, which is shown by yellow color, the mass entering the control volume is 7 kg and mass which is leaving the control volume is 2 kg. So the net change in mass within the control volume is equal to 7 minus 2, which is equal to 5 kg. Now we will find out what is continuity equation. By principle of conservation of mass, now we have seen that mass entering is equal to mass leaving plus increase of mass in the control volume per unit time. For steady flow, we know that the change in the parameters with respect to time will be constant. That means at whatever instant of time we measure the parameters like density, pressure, etc., they would remain constant, they won't change. So for steady flow, there won't be any increase in the mass within the control volume. So this term won't be there for the steady flow. So we can write mass entering per unit time is equal to mass leaving per unit time, as there won't be any increase or decrease of mass within this control volume. So for this figure, we can see that at section 1 there are the parameters shown as P1, V1 and A1, and for section 2 pressure is P2, velocity is V2 and area is A2. And the mass of fluid entering per unit time at section 1 is equal to mass of fluid leaving per unit time, and this will be for section 2. For incompressible flow, we know that density remains same. That means density is constant, it won't change. We can write mass entering is equal to density into discharge entering the control volume. We know that discharge is equal to volume of fluid entering per second. Volume divided by time is nothing but Q. Similarly, we can write mass leaving the control volume is equal to density into discharge leaving. Now, the mass entering will be equal to mass leaving, as there won't be any increase or decrease in the mass. So, Q entering is equal to Q leaving, as density is same. So, we can write Q1 as A1 V1 and Q2 as A2 V2. And this is what is the continuity equation for steady incompressible flow. And this continuity equation can be applied to pipes whose cross section varies along the length. So here we can see the pipe of varying diameter. So at section 1, if the diameter is D1, at section 2, the diameter of the pipe is D2. So it is a converging pipe. Diameter is decreasing along the length. If we use continuity equation, that is A1 V1 is equal to A2 V2, we will be able to find velocity at section 2 by using equation V2 equal to A1 V1 divided by A2. And similarly, the same equation can be used to find velocity at section 2 for a diffuser wherein the diameter is increasing. It is a diverging pipe. And continuity equation can also be used to find velocity in pipes starting from a junction. So here there are 3 pipes, number 1, 2 and 3, and this is what is the junction. The total mass flow into the junction will be equal to total mass flow out of the junction. The mass flow into the junction will be M1, which will be ρ1 Q1, that is equal to ρ2 Q2 plus ρ3 Q3. And if we consider that the density of the fluid flowing through all the 3 pipes is same, then ρ1 equal to ρ2 equal to ρ3. So this same equation reduces to Q1 equal to Q2 plus Q3. And we know that discharge is area into velocity. So it is A1 V1 equal to A2 V2 plus A3